Welcome to the component 2 task book, question 5, animal transport. Before competing, athletes often train at high altitudes for several weeks, after which their red blood cell count increases. The table shows these changes. So what we've got in the table, we've got an increase in altitude and we've got an increase in the number of red blood cells. Calculate the percentage increase in red blood cells in the athlete after several weeks at 6,000 meters. So this is just a typical percentage increase calculation, and we've done these on the videos before. So percentage increase is the increase, so find out what that is, divided by the start value times by 100. So here, percentage increase equals the increase. Well, what is the increase? It's gone from 5 to 6.2. So you can do that in your head, that's an increase in 1.2. If you weren't doing it in your head, you'd go 6.20 minus 5.0 in your calculator. But that is equivalent to 1.2. And you divide that by the start value. What's the start? It's not 6.2, that's the final value. So the start value is 5.0. And then times that by 100. And when you put that into your calculator, that comes out at 24%. So percentage increase calculations are always the same. You just need to commit that equation to memory and you'll nearly always get it right and get the 2 marks. Explain the benefit of the increase in red blood cell count. So all you're doing is remembering what the red blood cells are, what they contain and what their job is, and why this is of help to these athletes. Well, why is this happening? Because at high altitude it's a lower partial pressure of oxygen and there's lower concentration of oxygen in the air. So we don't even need to say it as complicated as that. We just need to say lower oxygen levels at high altitudes. So lower oxygen levels at high altitudes. But here's the real answer. What is the benefit? Well, we're going to get more red blood cells, more hemoglobin and more of whatever that job does. So more red blood cells, more hemoglobin. So we're going to get more oxygen carried by hemoglobin. So hemoglobin carries oxygen, so more oxygen carried. Why do we need this oxygen? So that we can maintain our aerobic respiration and for the athlete, the running. So maintains aerobic respiration for athletics. And in there, any 3 of those points would do. Here's a graph. We have got myoglobin A right over to the left and 2 hemoglobins B and C. The graph is a typical oxygen dissociation curve, partial pressure of oxygen on the bottom, so that's like the concentration of oxygen in whatever environment these are in. And we've got the saturation of hemoglobin with oxygen. So this is how much oxygen is actually attached to hemoglobin. So if we've got hemoglobin at 0, we've got our hemoglobin, quaternary structure of protein. At 100% we've got hemoglobin, our quaternary protein. At 0 there's no oxygen attached, whereas at 100% we've got 4 O2s attached to our hemoglobin, and in between 50% I'd have the equivalent of 2 hemoglobins attached. So that's what that scale means. Name the form in which oxygen is transported in the red blood cells. Well, it's already led us into talking about hemoglobin, but which form of hemoglobin is it? So it's just a name for when the oxygen is attached. So it's oxyhemoglobin. And with these graphs, I typically ask you a couple of questions just so that they can test your graph reading skills. State the percentage saturation of myoglobin at a partial pressure of 2 kilopascals. So tell us what this thing is on the left when we've got a certain number here at the bottom, and it was 2. So we are going to draw a line up with our ruler from 2. Try and get it as straight as possible. Pretty tricky. And then do a line across. Again, trying to get that as straight as possible. And when we do that and read off this scale, we're getting just above 90, so I would suggest that's 92. And indeed that's the answer. But they'll go plus or minus 2 there, so anything from 90 to 94 will do. However, I will put the correct answer 92. What's the units? Percent. Which of the curves B or C shows the greater dissociation between 9 and 12 kilopascals? So 9 and 12. So 9 and 12. We've got curve B. So B is actually fully saturated with oxygen. C, well, C is a bit less than fully saturated. So C is not fully saturated. So the question is, which of B or C shows greater dissociation? Well, B is not dissociated at all, and C is slightly dissociated, so the answer's got to be C. Curves B or C could represent those for fetal or maternal hemoglobin. State which curve could represent fetal hemoglobin from B or C. Well, I always remember curves to the left are llama, lugworm, little baby, L, 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 L. So we're going left for our examples of organisms in a low oxygen environment. So we go, right, let's apply that. Let's read the question again. Fetal and maternal hemoglobin. So which is fetal? It's the one to the left. So we're going to have curve B there. Reasons for that, well, it's left of the other one that it mentioned, C, so that's a good enough reason. And we'll always say in these questions, you know, the curve, the hemoglobin has got higher affinity for oxygen. That's our phrase that we're nearly always going to bring out in these situations. So I'm going to say curve B. Why? Well, if we're comparing it to C, it's left of C. So B is left of C. B, hemoglobin has higher affinity for oxygen. Explain how this is an advantage to the fetus. Well, you need to remember that the fetus doesn't have access to its own oxygen via its lungs, so it has lungs, but they're not functioning. The blood circulation in the fetus, the hole in the heart, ensures that the blood just goes around to the rest of its body and doesn't go to the lungs that aren't functioning. So it's got to get its oxygen from somewhere, and it indeed takes the oxygen from the mother's blood. Even though they don't mix, they come into very close contact. So the first point is the fetus needs to take oxygen from the mother's blood. So it takes oxygen from the mother's blood. And if we look at B and C, then at any partial pressure at all of oxygen, it will take oxygen from the mother's blood because it's got higher affinity. So it takes oxygen from the mother's blood at all partial pressures of oxygen. So if you can imagine if this B curve was on top of the C curve, so in the same place, then there would be a different affinity. So they would both be attracted to oxygen in the same amount, so you wouldn't get transfer across. We've got those two marks, but the third mark is just making that point, so we'll add that as well. So if the same, or indeed to the right, as others, hemoglobin, then oxygen would not transfer. But those first two are the points that you should really be making. Myoglobin is an oxygen carrying pigment found in muscle cells. With reference to the graph, suggest a function for myoglobin. So on the graph, myoglobin, curve A, so right over here to the left. So what does that mean? That means that it only releases its oxygen at these very low partial pressures of oxygen, and that'll be after hemoglobin has released its oxygen. So just really when the partial pressure is very low and when this oxygen is most needed. So that's why it can act as a store of oxygen, because it's not going to give it up very easily. So that's its job. So it acts as a store of oxygen. It's got high oxygen affinity, so it holds on to its oxygen. So it's got high O2 affinity. We're going to mention that phrase again. I always say affinity for oxygen. holds onto oxygen even at low partial pressures. So even at these very low partial pressures, say there, it's still quite saturated. So only releases at low partial pressures. Only releases oxygen at very low partial pressures. And that is after normal hemoglobin has released oxygen. And why here? Well, what's the purpose of this? Well, it's to maintain aerobic respiration in muscles. So maintains aerobic, and I'm always going to say aerobic because that's the type of respiration using oxygen. So maintains aerobic respiration. I'll just put in muscles. And that's how to read a dissociation curve.